Hello everyone, I'm Chaojian, a PhD student advised by Professor Yingyan in the USA lab at Georgia Tech. I'm very excited to present our work RT-NeRF, real-time on-device neural radiance fields towards immersive AR/VR rendering. As well recognized in the field of computer vision, neural radiance fields or NeRF is a powerful tool that can generate arbitrary new views of a specific scene given the input of sparsely sampled images of the same scene. To understand its working principles, let's take a look at the state-of-the-art efficient NeRF pipeline. In particular, to render each pixel, a ray will be emitted from the origin of the view. After that, the sampled points along the ray will be applied to a neural network to obtain the corresponding features of each point. Finally, such features from different points along the same ray will be aggregated to output the finally rendered color of the pixel. Motivated by NeRF's photorealistic rendering quality, real-time NeRF is increasingly demanded to enable numerous emerging applications, such as virtual meetings, metaverse, and autonomous driving simulation, which often require both high rendering quality and real-time rendering throughput. However, there exists a broken link between the achievable efficiency of the state-of-the-art efficient NeRF techniques and the desired real-time NeRF of the aforementioned applications. In particular, the first limitation is the large memory requirements of the state-of-the-art efficient NeRF, which can be as large as 15.4 gigabytes, while an Oculus Quest 2 VR headset, one of the most popular AR/VR devices, has only a total of 6 gigabyte memory. As an exciting heads up, with our proposed RT-NeRF, we can reduce the memory requirement to less than 1 gigabyte. The second limitation is the low throughput that can be achieved by the state-of-the-art efficient NeRF. Although more than 13 FPS is required to enable real-time immersive interactions, rendering 800 by 800 images on a GPU using the state-of-the-art efficient NeRF can only achieve a throughput of 0.01 FPS. As another exciting heads up, our proposed RT-NeRF can boost the rendering throughput to more than 13 FPS, achieving the first real-time rendering speed for edge applications. Before developing our proposed techniques, we first identified the efficiency bottlenecks by profiling the state-of-the-art efficient NeRF solution. Here we show the runtime breakdown. Specifically, the first step of mapping pixel to rays costs only less than 1% of the total rendering latency. The second step of querying the features of points along the array costs more than 19% of the total rendering latency. The final step of rendering pixels colors costs around 5% of the total rendering latency. The profiling results clearly indicate that more than 90% of the rendering latency is spent on querying the features of points along the arrays. After conducting a detailed analysis, we identified two key bottlenecks that cause the dominant latency of this step. The first bottleneck is the time needed to locate the pre-existing points in the 3D scene. The second bottleneck is to compute the points embeddings based on the results from the step of locating pre-existing points. Let's zoom into bottleneck 1 to better understand the cause of the inefficiency. To render each pixel, a set of points will be sampled along the corresponding ray, but not all sampled points will hit the real object. To compress the rendering cost, the state-of-the-art efficient NeRF will query those sampled points' existence based on a 3D binary occupancy grid. In particular, if the queried result is 0, then the following steps of the sampled points will be skipped. Otherwise, the sampled points will be processed with the following steps. As such, the access to the grid highly depends on the object in the scene, leading to irregular accesses to the occupancy grid. We identify that this causes the inefficiency in the bottleneck of locating pre-existing points. This is because rays can come from any directions. Thus, we cannot predict the access patterns when we sweep different arrays to render their corresponding pixels. Next, let's zoom into bottleneck 2. After the sampled points that can be escaped are identified, the algorithm will be processed to compute the embeddings of those unscaped pre-existing points in order to obtain their density and color information. Existing SOTA efficient enough, those embeddings are directly fetched from a 3D decomposed grid based on the corresponding point's location, as shown in this figure. We identify the cause of the inefficiency in this bottleneck of computing pre-existing points embeddings is that the sparse decomposed embedding grid is treated as a dense one while being executed, ignoring the fact that it is naturally sparse because objects are sparsely placed in 3D scenes. In other words, the sparsity was not leveraged for potential efficiency. To tackle the aforementioned bottlenecks towards real-time neural rendering, we propose algorithm hardware code design framework called RT-NeRF. Specifically, in the algorithm level, to alleviate the aforementioned bottleneck 1, we propose a new efficient rendering pipeline which enables looping over the non-zero values of the occupied grid with fewer and more regular accesses to the occupied grid. In the hardware level, to alleviate the aforementioned bottleneck 2, we propose a dedicated accelerator that integrates a hybrid sparse encoding scheme and the bidirectional trace to leverage the aforementioned sparsity in the decomposed embedding grid for boosted efficiency. Next, let's take a look at our algorithm contribution, meaning the proposed efficient rendering pipeline. The core idea of our proposed efficient rendering pipeline is to loop over the non-zeros of the occupied grid instead of emitted rays by utilizing the corresponding 3D geometry. The motivation is that in a rendering pipeline with such a looping order, we can access the occupied grid with regular patterns because its sparsity pattern can be null during training and thus known during rendering. Therefore, points that are not pre-existing and the corresponding cubes with zero values will never be accessed in such case, thanks to our proposed efficient rendering pipeline. However, simply looping over the non-zeros of the occupied grid can cost more than the existing baseline due to the needed operators to locate which points are inside each non-zero cube. In particular, such operators need to loop over all sampled points for each non-zeros of the occupied grid because the sampled points are irregularly placed in the 3D space. Thus, we need to figure out a way to more efficiently locate which points are inside each non-zero cube. Thanks to the fact that all the arrays are regularly placed in the plane to be rendered, we can locate which points are inside each non-zero cube in that plane. To do so, for each cube within the occupied grid that includes non-zero values, we approximate it as a ball for easy computation in the following step. After that, we project the ball into the plane of the pixels to be rendered. Based on the corresponding ball in the 2D plane, we can select the pixels inside the projected ball because they are regularly placed in the plane. Finally, a ray is emitted from the origin of the view to pass the selected pixels, and we compute the intersecting points between the ball and the ray in the 3D space. The simple points between the intersecting points are pre-existing points that we are looking for. As such, our proposed rendering pipeline leads to fewer and more regular accesses to the occupied grid while maintaining the rendering quality. Now let's take a look into our hardware contribution, in which we proposed a dedicated accelerator integrating a hybrid sparse encoding scheme and a bidirectional tree. In our proposed hybrid encoding scheme, we use different encoding formats for the dense and sparse matrices, which represent matrices with less than 18% sparsity and more than 18% sparsity, respectively. The reason why we need a hybrid sparse encoding is that the sparsity patterns among different types of weights and among different data sets can be imbalanced. For example, in the data set we considered, the sparsity ratio can range from 4% to 92%. With such an imbalanced sparsity pattern, using a uniform sparse encoding scheme is suboptimal. As such, it is critical to consider a hybrid sparse encoding scheme. Existing accelerator works has explored different encoding schemes for achieving the smallest storage size for different sparsity ratio. In other words, bitmap-based and coordinate-based encoding schemes for dense and sparse matrices respectively. However, despite their saved storage size, these encoding schemes either require varying decoding latencies that will reduce overall decoding efficiency, which is the cases for the bitmap-based encoding scheme, or have a lower decoding resource utilization that will increase the required chip area, which is the case for the coordinate-based encoding scheme. Thus, to simultaneously achieve a small storage size, high decoding throughput, and high resource utilization, we propose a new hybrid sparse encoding scheme that leverages the advantage of the two existing sparse encoding schemes. In other words, bitmap-based and coordinate-based encoding schemes, while at the same time addressing their disadvantages to achieve real-time on-device NeRF acceleration. This page further summarizes the disadvantages when directly using the two existing sparse encoding schemes. Now we will dive into the reasons why there exists no decoding throughput or low decoding resource utilization issues in existing decoding schemes in the following slides. If bitmap-based encoding is adopted and the sparsity ratio is less than 18%, we need to calculate how many non-zero elements possess the target element in order to decoding the target one. As such, the decoding latency depends on the location of the element to be decoded, which can introduce potential computation idleness and a low decoding throughput under the worst or a large decoding latency. On the other hand, if the sparsity ratio is higher than 18%, we need to adopt a search tree that represents the coordinate of the non-zeros that is utilized to decode the coordinate-based encoding scheme. However, we observed that there exists underutilization while decoding if the matrices are too sparse to utilize the full search tree. To tackle the issues of data-dependent varying decoding latencies in the bitmap-based sparse encoding scheme, we propose a new bitmap-based sparsity encoding format for the matrices, which has a fixed decoding latency. As shown in this figure, the proposed bitmap-based sparsity encoding format contains a newly introduced matrix pointer vector on top of the sparse bitmap matrices and the array of non-zero elements in the vanilla bitmap-based encoding scheme. The newly introduced matrix pointer vector is to store the addresses of the first non-zero element in each row of the sparse matrices. Thanks to the proposed bitmap-based encoding format, the maximum search latency for any element location in the sparse matrix is fixed. In other words, 3 cycles in our design, eliminating potential computation idleness that limits the achievable end-to-end latency. To tackle the underutilization issue when the matrices are too sparse to utilize the poor search tree in the coordinate-based sparse encoding scheme, we proposed bidirection trees to boost the utilization. Specifically, such a tree has 2 adaptive modes. In particular, the first mode is a pure adder tree to perform aggregation operators for computing the embeddings of unskipped points in our proposed rendering pipeline. The second mode is a mixture of the adder tree and search tree for the cases when the matrices are too sparse to utilize the full tree. This mode boosts the utilization by sharing the same hardware resource for different operators that perform the aggregation for computing points embeddings and tree search for decoding sparse matrices. The reconfigurability of the bidirectional tree is achieved by simply tuning off or tuning on or off the corresponding path in each node. To evaluate our proposed RT-NeRF, we consider 8 scenes from the NeRF synthetic dataset, and our baselines include 2 edge devices and 3 cloud devices. When comparing our proposed RT-NeRF with baseline edge devices on different datasets, we can observe that our proposed RT-NeRF can consistently achieve 3,000 times speed up than the baseline, more exact. And to the best of our knowledge, this is the first time that NeRF solutions can achieve real performance for edge applications. When comparing our proposed RT-NeRF with baseline edge devices on different datasets in terms of the energy efficiency, we can observe that our proposed RT-NeRF is around 4,000 times more energy efficient than the baselines on resource-constrained AR/VR devices. To summarize, thanks to the proposed efficient rendering pipeline from the aggregate level and the dedicated accelerator integrating a hybrid decoding scheme and bidirectional trees from the hardware level, our proposed RT-NeRF framework has delivered the first real-time neural rendering solution suited for edge applications. Thank you for your attention.